Welcome to The Explainer. Today, we're diving deep into one of the greatest technological quests of our time, building a practical, powerful quantum computer. You hear all about the promise, right? Well, today, we're talking about the problems.
And look, that promise, it's absolutely incredible. We're talking about the potential to solve problems that are literally unsolvable right now. Things like designing new drugs molecule by molecule, creating financial models that are unbreakably secure, or discovering revolutionary new materials. I mean, these are calculations that would take our fastest supercomputers today billions of years to even attempt. So the big question is, if the potential is that great, why don't we have quantum laptops yet? What's the holdup? Well, it turns out to get there, you have to run what we're calling the Quantum Gauntlet, a series of 4 massive interconnected challenges that stand in the way of this revolution. Okay, so the very first challenge, it's a physical one. It's a hardware race. Right now, scientists all over the world are in this massive competition to find the best possible way to build the fundamental component of a quantum computer, the qubit. And the two leading approaches, well, they couldn't be more different. On one side, you have superconducting circuits. They're fast, and companies have made huge strides in scaling them up. But they're also incredibly fragile. They lose their quantum magic almost instantly if they interact with the outside world, a pesky problem called decoherence. Then on the other side, you've got trapped ions. These things are fantastically stable and precise, but figuring out how to control thousands of them together, that is a monumental engineering headache. And this table, man, it really lays out the brutal trade-offs. As you can see, there's no single clear winner. Take a look at scalability. Superconducting qubits are on top, and that's a big reason why companies like Google and IBM back them. But then look at coherence time, which is just how long the qubit stays quantum, and they're at the bottom of the list. It's this constant, frustrating balancing act. You're basically just picking your poison. And that fragility leads us right into our next challenge. Because even if you pick the best hardware, every single type of qubit is so sensitive, it's almost hard to believe. The slightest vibration, a tiny change in temperature, a stray magnetic field, any of it can introduce errors and completely destroy your calculation. And this brings us to challenge number 2, which is maybe the biggest one of all, reliability. Okay, so here's the thing. In theory, we actually have a solution for this. It's this really beautiful piece of physics called the threshold theorem. And it basically says, yes, your physical parts will always be faulty, but if you can get those errors below a certain critical point, you can actually use clever codes to build a perfectly reliable machine out of a bunch of unreliable parts. It's kind of mind-blowing, and it gives us hope that this whole thing isn't impossible. So how do they do it? The process is called quantum error correction, and it's a constant, high-speed race against noise. First, you have to cleverly check for errors without actually looking at the quantum data, because that would destroy it. This gives you a syndrome, kind of like symptoms of a disease. Then, a classical computer has to rapidly decode that syndrome to figure out what went wrong. And finally, you apply a precise pulse to correct the error. And you have to do this again and again and again, thousands of times every single second. But, and this is a huge but, here is the absolutely staggering catch. This error correction comes at an immense cost. To get just one of those perfect, reliable, logical qubits that you can actually use for a calculation, you might need thousands, maybe even 10,000 of the noisy physical qubits we can build today. I mean, think about that. That overhead is just massive. Okay, so we've got a hardware challenge, we've got a reliability challenge, but let's say we figure that out. Who's going to design, build, and actually program these things? This brings us to a very human problem, the talent chasm. And this chart, wow, it really shows you the scale of the problem. A McKinsey report found that for every 3 quantum jobs out there, there's only 1 qualified candidate. Demand is just crushing supply. Projections are saying that by 2025, less than half of all quantum jobs might actually be filled. You just can't build the future if you don't have the people. So to fix this, there's this massive 3-pronged effort underway. You've got universities creating brand new quantum engineering degrees that mix physics and computer science. Then you have companies like IBM and Google opening up their software and creating free online courses to get more people coding. And finally, governments are pouring money into national programs to fund the next generation of quantum scientists. All right, let's imagine for a second we solve all that. The hardware, the reliability, even the talent problem. There's still one final, cold hard challenge, making it all commercially viable. Basically, who's going to pay for it and why? And this survey from Hyperion Research, it shows us exactly where things stand right now. look at this. The vast majority, something like 60% combined, are still in the let's just check this out and what could we maybe do with this phase. Only a tiny fraction, just 14%, are actually using them in production. Basically, we're still kicking the tires. That killer app? Nobody's found it yet. And why are they so cautious? Well, it all comes down to some really practical, real-world business hurdles. I mean, how do you even integrate this bizarre new technology into your existing data centers? How do you prove to your CFO that a multi-million-dollar investment is actually going to pay off? And which company do you even bet on when the winning technology is still a total unknown? These are the tough questions executives are asking. So, after running this gauntlet of 4 huge interconnected challenges, where does that leave us? Honestly, the whole field is caught in this fascinating tug of war between incredible, tangible progress and this deep-seated, persistent skepticism. On the one hand, you've got the optimists, and a lot of these folks are the ones in the labs, doing the work day in and day out. They point to the real, undeniable improvements we see every single year in qubit quality, scale, and error correction. For them, the progress is undeniable, and it proves these challenges are tough, sure, but they're solvable. But then, on the other hand, you've got the skeptics. And, they've heard these promises before. They point out that the goalposts for a truly useful, fault-tolerant machine always seem to be moving further away. They'll tell you that the finish line, well, it just never seems to get any closer. And all of this leaves us with the ultimate question, the one that hangs over this entire field. Are these just really hard engineering problems? Problems that time and money and a whole lot of brain power will eventually solve? Or is it something deeper? Are we brushing up against a fundamental wall where we actually need a whole new discovery in physics to take that next leap? And that, right there, is the multi-billion-dollar question that thousands of the world's brightest minds are racing to answer.